is made up of particles. There are different types of particles: electrons, quarks, or neutrinos. Particles move in the universe and can interact by exchanging other particles. The electromagnetic force, for example, is mediated by the exchange of photons. All these different particles are accounted for in what we call the Standard Model. It is currently our most precise mathematical description of the quantum world. It contains two main categories of particles: fermions, which mostly constitute matter, and bosons, which mostly describe interactions. At first glance, one might think that this is the ultimate theory, that the Standard Model describes everything. But unfortunately, there is another interaction that this model doesn't account for: gravity. On a large scale, we know that gravity is described by general relativity. Objects curve space-time, thus attracting other objects. As with other types of interactions, we expect that the curvature of space-time is made up of small particles at the quantum scale, quanta of space-time curvature called gravitons. But when we try to include the graviton in the Standard Model, the calculations give absurd results with infinite values that cannot be removed. We cannot describe gravity on the quantum scale. It is to solve this problem that physicists have been looking for new theories for more than half a century. In this video, we are going to build together one of the most promising approaches: string theory. The basic idea is quite simple. In the Standard Model, particles are described as small dimensionless points. We admit that these points do not all have the same properties to account for the fact that there are different types of particles. In string theory, we will assume that this is only an approximation, and that if we zoom in on the particles, they are all made up of a small string, sometimes open and sometimes closed. These little strings have tension, like tiny rubber bands, and they can vibrate. A guitar string can vibrate in different modes, harmonics. Likewise, our little strings can vibrate in different ways: 1 ripple, 2 ripples, 3 ripples, and so on. And the different vibrating modes behave on our scale like particles of different types. When we perform the calculations, we discover in particular that some strings behave like photons, and better still, some like gravitons. Starting from the sole principle that particles are tiny strings with tension, we already explain why there are different types of particles. And we naturally predict the existence of the graviton, thus describing gravity at the quantum scale. We now want to understand how these strings evolve through the universe. For that, we will use the same principles as our current models. Imagine that we throw an electron at a target. The electron propagates like a wave, and when it reaches the target, we can't know for sure where it will materialize. At the quantum scale, the same experiment can give different results. We can only predict the probability of observing such or such result, and the goal of physics at this scale is to determine these probabilities. The mathematical approach to determine the probability of observing a particular result is to consider all possible scenarios that lead to it at the same time. We sum all trajectories, but also all possible interactions. For example, an electron can emit a photon, then reabsorb it, or 2 photons, or even 3. In all the scenarios that we consider, we manually decide to allow such or such types of interactions to reproduce what we observe in reality. And by summing all these scenarios, we obtain the desired probability. In string theory, the approach is the same. However, the particles are no longer points. A point traces a trajectory over time, but a string traces a surface. And to describe the evolution of a string in a probabilistic way as in quantum physics, we will consider all possible geometries that the string can trace over time. It can follow a specific trajectory, vibrate in a certain way, but also duplicate itself, which amounts to emitting a particle, or recombine, which amounts to reabsorbing the particle, forming a geometry with a hole. By summing up all possible geometries, string theory automatically includes interactions. There is no need to add them manually. Incidentally, interactions in the standard model were local. The emission of a photon was instantaneous, for example. In string theory, interactions are now continuous. Particles are no longer emitted instantaneously, but gradually. This gets rid of the infinities that we obtained when we tried to include the graviton in the standard model. In this way, string theory not only predicts the existence of the graviton, but it also allows us to calculate how it interacts with other particles, and therefore to describe quantum gravity. So far, the theory looks very promising. It explains why there are different types of particles. It predicts that they can interact. And it includes a quantum description of gravity. Unfortunately, at this stage, the model exhibits 3 problems. First problem: all the strings behave like bosons, such as photons or gravitons. In our world, there is another category of particles, fermions, such as electrons, but so far our model does not predict such particles. Second problem: one of the particles predicted by the theory is what we call a tachyon. Its mass appears to be an imaginary number, the square root of a negative number. It is a mathematical problem that we must get rid of. Finally, the third problem. Our space-time has 4 dimensions, 3 dimensions of space and 1 of time. But this theory only seems to work in a universe with 26 dimensions. At this stage, string theory seems very far from describing our universe. To solve these problems, we'll have to push the theory a little further. To include fermions in our model, the idea is to add spinors on the strings. They are the mathematical ingredient that already described fermions in the standard model. By simply adding spinors to the strings, we solve 2 problems. The model now predicts the existence of fermions, and it no longer predicts the tachyon, the particle that was problematic. This more complete theory is called superstring theory. In fact, now that we added spinors, our theory exhibits a fundamental symmetry between fermions and bosons. In a way, it predicts that there would be as many bosons as there are fermions. This is called supersymmetry. What about the third problem? Before we included supersymmetry, the mathematics required a 26-dimensional universe. Now, superstring theory requires a universe with 10 dimensions. Unfortunately, this third problem is not resolved. The theory does not seem to fit our universe, which only has 4 dimensions. Yet, so far the model was very promising. Should we abandon it for all that? If they exist, where would these 6 missing dimensions be? One possibility is that our universe could just be a three-dimensional slice of a larger, nine-dimensional super-universe. Another possibility could be that the 6 dimensions that we do not observe are curled up on themselves. To understand, let's imagine an ant walking on a straw. The straw has 2 dimensions. The ant can walk back and forth, and left to right, around the circumference of the straw. But if we zoom out enough, we only notice one of the 2 dimensions. The second one that curls around the straw is very small and cannot be seen on this scale. In string theory, we can assume a similar phenomenon. Our universe would have 9 dimensions of space, but 6 of them would be very small dimensions curled up on themselves, so that we do not see them on our scale. This hypothesis may seem a little far-fetched. Is it reasonable to assume the existence of dimensions that we do not observe? But it turns out that the existence of additional dimensions is a very interesting question that suggests phenomena that we might observe. For example, we could imagine a massless particle that moves at the speed of light, but partially inside a compact dimension. From our point of view, we do not see this dimension, and therefore the particle seems slower to us. We only observe part of its full motion. It seems slowed down, as if it had a mass. The idea of additional compactified dimensions thus suggests a fairly simple mechanism through which some particles might exhibit a large mass. However, it would currently require too much energy for us to create them in our particle accelerators and confirm or not their existence. The presence of these additional dimensions also allows a much more varied range of vibrational modes, and therefore a greater diversity of potential types of particles. In addition, there are a multitude of different ways to curl up 6 dimensions, and each possibility will predict a different universe, where the strings can adopt different vibrational modes and therefore behave like different particles. By carefully choosing the way in which these 6 dimensions are compactified, we can adjust our description so that it predicts the same particles as those we observe in our world. That said, among the myriad of possibilities, it is not yet clear why our universe would contain the particles of the standard model, rather than some other possibility. According to some still speculative hypotheses, the geometry of the universe might even have varied over time, transitioning from one compactification to another, and the laws of physics could thus have changed during the first instance of our universe. To conclude, string theory remains to this day a speculative model, very difficult to test experimentally since the strings would be incredibly tiny, and which is only one approach among many others in the quest of finding the ultimate theory. However, it is still one of the most promising models, whose insights have far exceeded its original goals. Strings allow us to describe gravity on the quantum scale and open doors to the study of black holes. They help develop several fields of mathematics and get a better understanding of the standard model itself. String theory even offers hypothetical candidates for particles, such as axions, to potentially explain dark matter. That said, there is still a lot of research to do. In particular, the aspects of string theory that are best understood rely heavily on supersymmetry, which tends to predict the existence of additional particles which we don't seem to observe yet. There are some compactifications that would explain that we don't observe supersymmetry, however these are still very rare and not well understood. Finally, to venture even further, there actually exist 5 different versions of superstring theory, describing different types of universes. We can show mathematically that these 5 theories are in reality approximations of a single, more complete model, describing a universe with 11 dimensions. M theory.